comma v to be integrable functions, and I want them to be real valued. So sometimes it will look like this. And I want alpha to be a real number. And I should say here that in the book, he actually does it also for extended real functions. And I want to be, if not really lazy, then more convenient, simply because I want to talk about the sum of two functions. I want to take these two functions and add them together. And it's a mess if they are extended reals, as we already talked about. The book is careful enough. He does say that whenever they are defined, blah, 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 but it just makes the whole statement more ugly, in my opinion. So therefore, I make the convenience to restrict the assumptions a little bit in the book and assume that they are both real values. And I really want to emphasize that L1 should be a real value set of functions. Okay. So under these assumptions, then what do we have? Let me take it here. Firstly, we have that, so u is integrable and alpha is a real number, then alpha times u is also integrable. And the integral alpha u to u is equal to alpha times integral u to u, like this. And this does not seem like a very surprising statement. It certainly should be true. If you take a function that is integral and multiplied by some number, 14 or minus 27, it should remain integrable, and that number, 14 or minus 27, you should be able to put it out in integral. We'd be very unhappy if this was false. And it is true. However, as we shall see, it is not very difficult to prove, but it is a little bit tricky. It's surprisingly tricky. Also for the next one, actually, it says that the sum of u and v are also integral. This is really where I would like my functions to be real valued. And the integral u plus v in u is the sum of integrals. And again, this statement here is, I would again say, surprisingly tricky. Then there is a statement that I don't think I will prove, I will just make that max of the two functions and min of the two functions are also integrable. There is no statement about the integral here. You have no idea what the integral is. But the only statement is that they actually belong to this space. But no statement about what the integral is. Then if u is less than v, as real functions, not that they are processed just like this, you can conclude that the integral of u in u is less equal to the integral of v in u. So the integral is monotone, also in the real case. Fifthly, and this is very useful, if you take the integral, which is a real number, and take the actual value, which now is a positive number, then this is less equal to the integral of actual value of u. This is a very, very much used inequality. It's very important. So this is the theorem. So let's try to prove it. And let's begin by part one. So part one is this thing about first show that alpha times u is integrable. And let me already here say that we are using this rather simple observation in this theorem here, because if you were to prove one, then what you might do is you simply say, what does it mean for alpha u to be integral? Well, it means that the viscous with positive part of alpha u and negative part of alpha u. And you can do it. It's just a little bit tricky because the positive negative part of alpha u is a little bit, well, it's a little bit surprising what it is. But you can somehow get around it more easily by saying that by simply using this statement here. It's much bigger to use this statement here. So what we do is we consider the integral of alpha times u, and this is of course the same thing as alpha absolute value times u absolute value in u. And now this is a positive number, this is a positive function. So we can take this number outside using the techniques of the previous chapter. So this gives alpha absolute value times integral u in u. And this is now finite. And this is finite. And product of two finite numbers is finite. Hence, alpha u is integral. Okay. And then we want to calculate the integral, and now we have to consider the positive and the negative part of alpha u. So let me kind of be wasting space here. Let me write it down so I get it correct. So if alpha is a positive number, then alpha u positive part is, not surprisingly, alpha times the positive part of u, and alpha u negative part is again alpha times u negative. However, if alpha is a negative number, then the positive part of alpha u is minus alpha times the negative part of u, and alpha u negative part is minus alpha times the positive part. So note here that in the negative case, this is a positive number times a positive function. So this is called positive. Minus alpha is a positive number times a positive function. This is all positive. And I can maybe make a drawing to, I guess you're not surprised to see these equations here. They are what you would expect. But let me just try to convince you a little bit why. This holds just one example. So let us take, say, sine of x. It's a good function that takes both positive and negative values. You know it well. And let me just take it from minus pi to pi. It goes like this. Sort of. This is our function u. And what is, suppose now that our number alpha is minus 2. So what is then alpha times u? That is minus 2 times sine of. So that then goes twice as high, like this. So this is then minus 2 times u. Okay, so what if we take the positive part of this and let's say breathe it positive see that true times u minus is equal to the green function here, which is minus 2u plus, and similarly to the other one. So at least now in this drawing you can see that these things are true. So that's really the only big thing about this. Okay, so with this, let me then try to quickly prove the statement, and let me take a break on that, and I'll only prove it for negative alpha, which is show, so I'll prove for alpha negative that the integral alpha u du is equal to alpha u du. Okay, so what we do is we say that integral alpha u du is also exercising using definitions here. This is will be the integral of alpha u positive part minus integral alpha u negative part. Then we use the formulas that this is equal to that was minus alpha u minus mu minus alpha u plus mu. And then, so now this is a positive number, positive function, so we can use the results of the previous section to take out these positive numbers. So hence this is the same as minus alpha integral of mu minus mu plus, okay, minus and minus alpha integral mu plus mu like this. And then we rearrange minus minuses plus, so I take this sum first. So this one goes here, and this one goes here, and this minus becomes minus. Like this. And then I put alpha outside the parentheses. And we see what is inside of here is precisely by definition the integral of u. Like this. So everything works out. So it does, not very difficult to prove, but I would say maybe surprisingly difficult to prove, since the statement seems very straightforward. Okay, I take a break here. It is 2 minutes past my clock, so in 17 minutes.